My name's Colin Gore. I'm currently in my third year of a doctoral program at the University of Maryland, and I'm in the Materials Science and Engineering department. My project is developing coking-resistant, stable anode materials for fuel-flexible solid oxide fuel cells. Solid oxide fuel cells are a particular variety of fuel cell. Fuel cells are electrochemical devices that convert chemical energy in the form of a fuel directly to electrical energy. They are inherently more efficient than other technologies like internal combustion engines or steam turbines, because in a fuel cell you're going through an electrochemical process rather than a heat-based process, and you're harnessing the electrons directly to create electricity. When people think of fuel cells, they commonly first think of proton exchange membrane cells. They are certainly more common, at least in the media, but they have a big drawback, which is that they require very pure hydrogen to run, because they have a membrane and they take the hydrogen from the fuel and take it through the membrane as protons. So they are very intolerant of anything else but hydrogen basically being in that fuel stream. Solid oxide fuel cells, on the other hand, operate by taking oxygen through the membrane. So they can take oxygen from the air to essentially any fuel that will oxidize. This is critical to why solid oxide fuel cells, above any other variety of fuel cell, are directly applicable to energy technology now, because our whole infrastructure is based off of gasoline and diesel and coal and other hydrocarbon fuels that take a lot of energy and processing to turn into hydrogen, and it makes a lot of sense to use an electrochemical cell that can utilize these fuels directly. My research focuses on the anode portion of the cell. The anode is the part of the solid oxide fuel cell that is in contact with the fuel gas. And so many challenges pertaining specifically to the fuel can be dealt with by altering the anode material. Key challenges are just the overall stability of the material, since fuel cells will be operated for thousands of hours at a time in power generation applications at relatively high temperatures. And they also have problems with coking. Coking is the deposition of carbon inside the porous parts of a fuel cell. Since we're using hydrocarbon fuels instead of hydrogen, the carbon can be deposited on the anode depending on the anode materials. The current state-of-the-art materials are based off of nickel cermets. So it's nickel and YSZ or some other ceramic material. And it turns out that the nickel catalyzes deposition of carbon. So it catalyzes this coking and causes very severe degradation of performance of the fuel cell. So by using different materials, either different metals or different architectures just of the anode, we can address both coking and stability problems for operation of the fuel cell on hydrocarbon fuels, which are essential to really making an impact immediately based on the current hydrocarbon infrastructure we have. having a fuel-flexible anode material for solid oxide fuel cells will allow them to integrate very effectively into our current infrastructure, which is a key benefit to this technology. Whereas other sustainable energy technologies require some big changes to our infrastructure, fuel cells have the advantage of really transitioning directly into the current gasoline and coal-based energy infrastructure that we have at the moment. I see two main classes of application for fuel-flexible solid oxide fuel cells. The shorter-term, easier technology to transition into is stationary power applications. So they would be smaller power plants essentially that could be scaled down to be just enough energy to power your home. These things could be in the basements of places that are pretty remote and essentially off the grid, being powered by natural gas or some other fuel source. And they can also easily be scaled up all the way to the megawatt scale and creating power for entire cities. And the scalability is just an inherent factor of the design of fuel cell stacks. So that is a quite convenient shorter term application. But there's a second group of applications in the transportation sector. They are a little further off because we need to also develop the other parts of the fuel cell, the electrolyte and cathode, in order to ensure lower temperature operation of fuel cells. So I would like to thank the Metro Washington chapter of the ARCS Foundation for acknowledging my research here at the University of Maryland with this fellowship. It's a real honor to know that my research in solid oxide fuel cells has the support of a group of scientists interested in sustainable energy and ensuring our energy future. And it gives me a great confidence boost in my research to go forward as a recipient of this fellowship.